자, you don't have to remember what J psi is, but here it states that J psi consists of charm quark and anti-charm quark. And quark has up-type quark, such as a charm quark, has electric charge that is 2/3 of the electric charge. An antiparticle, just like positron, is opposite to the electron. They have equal magnitude in electric charge, but it is negatively charged and positively charged. So the anti-charm has a negative sign on it. Sum of these two charges becomes 0. That means that J psi is electrically neutral particle. So this is electrically neutral particle, and these two charges are opposite, so it does not violate the conservation of electric charge. That's the most important point. Electric charge is a fundamental quantity, and it is exactly defined in such a way. So the number of significant figure in this is not Euler's number. Euler's number is 1 plus 1 over n to the n, limit n goes to infinity. It looks the same, but this is elementary electric charge that is exactly defined. The number of digits 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks there is 10 significant figures. However, it is exactly defined. It is hidden. The 0 appears to the infinity. So this is the exact number. It is not 10 significant figures. Electric charge of a proton is E, and electric charge of an electron is minus E. Electric charge of a neutron is 0. Neutron is electrically neutral. Electric charge Q can be detected. Is an integer multiple of elementary electric charge. Sure. This is a unit of electric charge. It is impossible to have 1/2 of electron. Sure, there are quarks that has a very strange amount of electric charge, but quark has never been observed separately. That is always included inside the hadron. For example, proton consists of up quark, and d quark. Up quark has 2/3. Down quark has a minus 1/3 of electric charge. The sum is E. Proton electric charge is E after the sum. Although a quark has a fractional electric charge, 1/3 or 2/3, a single isolated quark can never be detected experimentally. It is always confined inside a neutron or proton. Coulomb's law. Coulomb's law is either parallel or anti-parallel to the line connecting two electric charges, Q1 and Q2. The Coulomb force is along the radial direction that connects the two charges. It is very similar to the gravity that connects the two masses. These kind of forces, that is the line of force is parallel, and on the line that connects the two objects that sharing the forces is called central force. And both of them satisfy the inverse square law, 1 over r squared. The strength of the force that decreases as the distance of the two objects increases as a 1 over r squared. That is called inverse square law. Both Coulomb force and gravitational force, its curl is exactly zero. If we apply the Stokes theorem, the curl F equals 0. Therefore, integral of curl F on a surface, that is according to Stokes theorem, is identical to the line integral along a closed path that is the boundary of this surface. Because the integrand is exactly zero, this integral is zero. That's the reason why conservative force does not work at all if you return to the same point. That's the key point of the conservative force that we learned in the first semester. The work done by the Coulomb force along a closed path is always zero. That's the reason why it is a conservative force. The SI unit of Coulomb, SI unit of the electric charge is Coulomb, and that is identical to ampere multiplied by 1 second. Permittivity constant determines the strength of the Coulomb force, 1 over 4 pi epsilon 0, product of charges and distance between them squared in the denominator. This one has an uncertainty. However, as shown in this expression, product of epsilon 0 and mu 0 determines the strength of the magnetic force, and product of this is found to be 1 over speed of light squared. That was first noticed by Maxwell. And this product is exactly defined. The speed of light is this, and the number of significant figure in the speed of light is infinite. 1 over 4 pi epsilon 0 is also called the electrostatic constant, and the number is given in here, and this is uncertainty of the last two digits. Electrostatic induction, I hope you can review the original file for Y1. Pairs of uniformly charged identical hemisphere means just one exact half of a sphere. Spherical shells, so it is empty inside, of radius r, the radius is r, placed as shown in the figure. The blue one is negatively charged and the red one is positively charged. The centers are placed at minus a E1, so this is x-axis. E1 hat is along this direction, so they are in opposite. Because the uniform distribution is kept invariant, shells are not made of conductors. Sure, conductor redistribute the charge to make the electric field normal to its own surface. And if it is a closed one, electric field inside the conductor must vanish. And this is application of is closely related to shell theorem. However, if you apply the shell theorem, the distribution of electric charge must be spherical symmetry. One cannot apply the shell theorem, right? Because the charge distribution is not showing the spherical symmetry. Magnitudes of electrostatic forces are ordered. Magnitudes you can find just like the center of mass, center of charge, then you can count the distance. So this is nearest, this is farthest. So we have longer distance according to the inverse scale law, weaker, the middle, and the strongest. Electrostatic force is attractive, sure. They are of different sign. In electric charge, the force is attractive. In the case of gravity, they are attractive only. If the sign of the two charges are the same, the force is repulsive instead of attractive. 7. Shell theorem is valid for both the gravitational force and electrostatic force, right? One can apply the Shell theorem only if the charge or mass distribution is spherically symmetric, right? One should be careful with the possibility of a redistribution of electric charge due to the presence of another charged object when applying the Shell theorem in an electrostatic case. Yes, in the case of a gravitational force, we usually consider the case a celestial body that is a kind of rigid body. The mass is not to be redistributed according to the gravitational force. But in the case of electric charge can flow here and there once the electric field is created. So a little bit difficult than the case of gravitational problem. Spherical symmetry of a charge distribution can be destroyed due to the presence of other charges. Sure. For example, there is a plate, a conducting plate, and if a point charge is approaching, then induced charges will be created. Redistribution appears. So if there is such a status, then we cannot make use of the Shell theorem. Okay. If you consider this problem, there is a symmetry. For example, this one and this one, they are of equal, their charges are the same. Therefore, regardless of the charge inside, this, for example, A and A prime, their contribution of the Coulomb force on this object must cancel. That is true for this and this, and this and this. So this problem asks you the sum of the electrostatic force of this red one and blue one. And then, because they have a symmetry, only the sign is different, therefore, you have to consider the force between these two and multiply by a factor of 2. That's the key point of this problem. And the intermediate step to compute this are given in here. Number 9. A point particle charged with Q is at X under the presence of another charge, capital Q, at the origin. Capital Q is here, and there is a vector X, and there's a small charge Q. And electrostatic force on this object is this, and ER is the unit vector, unit radial vector, parallel to the vector X. We already learned in the first semester this inverse scale law with the central force. Central force, the force is along the line that connects the two objects. So in that case, the curve is exactly zero. Therefore, it produces conservative force. And if we have the force that is proportional to 1 over r squared as a central force, we know how to compute the potential electrostatic potential energy of the system. That is just 1 over r. Because the force is central, the orbital angular momentum of Q is central force conserved. Just like the motion of a planet around the star, sun, orbital angular momentum is conserved, right? That is related to the second law of Kepler's second law, angular momentum conservation. That is true for the electrostatic case. A point particle charged Q is at X under the presence of the following uniform charge distribution. Okay, you notice this is volume of a cube. So Q over V, and this volume is 4 pi 1/3 R cube, right? So electric charge Q is uniformly distributed over a sphere, field sphere. Okay, that means we can apply shell theorem. We assume that the charge distribution does not change, right? Find the full statement regarding this situation. If you are not familiar with the shell theorem, review X11 in KPOPE. The net charge of a whole charge distribution is Q, right? Q is over a radius capital R, within the radius R. The net force on Q at any X, that is whose magnitude is greater than the radius, yes, according to shell theorem, charge Q can be placed as the center. And if there is another Q with the distance R, then the force can be computed as just like the point-like case, right? In case this small charge Q is placed in here, for example, then the answer should be the distance between the two charges is this, and the amount of charge of this object is this, instead of the whole amount, because outside this shell, contribution is exactly zero. So in case you are inside the shell, then you have to count the charge, net charge, not the whole amount, but the amount contained within the small radius R. So over factor cancels, and that is just RQ. This is a small r, and capital R is the radius of this sphere. So in that case, we can find the charge should be corrected with this one, and by multiplying this factor, r squared cancels, and it is proportional to r. All right, so the net force becomes a zero if we substitute r equals 0. The electrostatic force between this charge and a point charge, when it approaches the center, there is no charge to communicate, so the answer is 0 when r which is 0. So in here, electrostatic force on Q disappears at x equals 0. All right. You have to train how to compute the electrostatic force from the electrostatic potential. That is a proportional, that is a scalar proportional to 1 over r. And these are detailed calculation table. So you can follow all these to reproduce the electrostatic force by computing minus the gradient of potential energy. And potential energy is much easier to compute rather than the Coulomb force that is a three-dimensional vector. Perhaps somebody does not know what gradient is. Gradient is nothing but the derivatives along the x, y, z axis, and this is a vector quantity. So x component of a gradient is the x partial derivative, and y component of a gradient is a y partial derivative, and z component of a gradient is a z partial derivative. And we can make use of chain rule to find this one. So you will find in detailed calculation in X20. Oh, a point particle charged with small q is at x under the presence of another charge. The very similar problem. This is involving the divergence calculation. Divergence is if f is a vector, e1 hat, e2 hat, f2, e3 hat, ef3. Divergence is sum of x derivative of x component, y derivative of y component, and z derivative of z component. Okay, so this is divergence. And divergence can be computed by using chain rule in terms of radius r, and then take the partial derivative with respect to x, y, and z. So you'll find the divergence absolutely vanishes. Okay, consider except at the point x equals 0. So at x equals 0, divergence diverges. 13, consider the spherical symmetric charge distribution centered at the origin. We have a charge q. We have a symmetry of charge distribution. Small q is infinitesimally small and therefore does not affect the charge distribution of capital Q. Okay, for all x satisfying x is greater than radius, then we can apply the shell theorem, and the distance can be used. Distance between these two objects appears in the denominator according to the inverse of scale law, and charge q, everything can be included, and small charge is outside of this shell, so net charge is a capital Q. If x is smaller than radius, then what we have to consider is the charge q should be this, not the whole amount. That means if small charge is at it here, the charge outside the radius does not contribute to the electrostatic force. Only the charge within the radius does contribute to the electrostatic force. That is the shell theorem. Number 14, spherical symmetric charge distribution. Okay, we have radius A, radius B. At A, we have charge plus Q. This is a sphere, and we have minus Q. For all x's satisfying x is greater than A, okay, here we put charge Q in outside. Then, according to shell theorem, this one communicate with this one with the distance, but what is the net charge inside? Sum of this is 0. That means this charge does not communicate with this sum of the two charges because of shell theorem. It is at 0, free of electrostatic force. Less than B, here, okay, you replaced this Q inside this. In this region, there is no charge. What we have is a charge in here and here. So the center and charge Q, you draw a sphere, and inside this sphere, there is no charge. Therefore, there is no electrostatic force. Only in this region, between minus Q and plus Q, you feel the charge. What charge is? You have minus Q inside, you have Q, and you have plus Q outside. And this charge communicate with this charge only, because this plus Q is outside of a sphere of radius r. So we have negative minus Q is used. In this region between A and B, the electrostatic force between the charge distribution and small charge Q is this one. Okay, 15. These two are related to the Gauss law. I told you divergence of the electrostatic force vanishes whenever x is not equal to 0. So you can compute the divergence over some volume. However, this one is always 0 except at x equals 0. So we can find there is origin where the electric charge is placed. There is a very tiny radius epsilon, and we can consider this a sphere, a very tiny sphere, except that among V, this is a general V, divergence, this integrand is exactly 0 everywhere else. And then this integral is this, and this small integral, the integral over a very tiny region, can be evaluated by making use of divergence theorem. Divergence of a volume integral is identical to this force, scalar product, and surface. That surface is the boundary of this tiny volume. And on the surface, this surface is proportional to the solid angle and radius square. And the force on this surface, according to the inverse scale law, we have r squared in it. Because r squared cancels, this very strange integral becomes trivial. It is just a constant. That is just the product of the charges divided by epsilon zero, permittivity constant. Finally, this one in here, we have charge Q is inside a tiny region of very small radius. And charge Q can be obtained by integrating the density and over the volume. And that is actually the Dirac delta function. That is, it looks complicated, but Dirac delta function is just infinite at x equals 0. I told you point charge has a finite charge, but volume is 0, approaches 0. So mathematically, density of the electric charge due to a point charge is infinite at that point. However, because the volume integral must give the net charge Q, this function is nothing but a trivial function whose volume integral is 1. Instead, it diverges at x equals 0. Finally, this one determines from this expression, this one determines a density of charge at the origin. Except that everywhere else where there's no charge, this divergence must vanish. And later, when we study Maxwell's equation, we will find it leads to the Gauss law.